Having a look at the examples that we've got here. The first one, we've got our dilation factor outside the function, so it's multiplying the entire function. And what that does is, and it is greater than 0, so it's going to dilate the function vertically by a factor of 2. The axis intercepts stay where they are. So the first thing we do is just draw them in. The reason for that is 2 times the value of the function is what we're graphing. If the value of the function is 0, then 2 times 0 is 0. Then we look for our critical points, such as this maximum here at -1.5, 1. The value of that increases by a factor of 2 to 2. That's confusing. Same with the next one. We've got a maximum at 1, 1. The value of the function at x equals 1 doubles to 2 as well. We can then have a look at our endpoint here, which has a value of 3. This is 3 here. That value doubles to 6. Notice that none of the x coordinates are changing, it's only the y coordinate. You can also do the same thing here. When x equals 4, y is 2, so it doubles to 4. When x equals 3, y is 1, and it doubles to 2. And from there, you join them up using the same curves, but stretching them out to the location they need to go. So this one stretches up to here and back, up and back, and then up in a straight line. And you can see that what's happened is it's as if the entire function has been stretched upwards this way. In green, I'm going to do a half of f of x to see what that looks like. So again, we find these critical points. Again, the axis intercepts will stay exactly where they are. This point at -1.5, 1 will be compressed to -1.5, a half. This point at 1, 1 is compressed to 1, a half. And our endpoint at 5, 3 is compressed to 5, 1.5, which is here. 4, 2 compresses to 4, 1. 3, 1 compresses to 3, a half. And then we draw those sections in with the same curves, this time just compressed. So that is that is a half f of x, and the red one is 2 f of x. And you can see there the effect of x being greater than 1 or between 0 and 1. In this second example, the scale factor is k, and it's inside the bracket, which means it's operating on every x within the bracket, which has the effect of compressing or stretching by a scale factor of 1 on k. So k equals 2, which is greater than 0, so therefore it's going to be compressed by a factor of a half. So what that means is every position that's on our graph is going to be halved. So starting from the left, we've got this position here at -3, 0. The -3 gets halved to -1.5. The 0 stays the same. This maximum here is at -1.5, so it gets halved to -3/4. This x-intercept gets halved to 1. This position of 5 is halved to 2.5. This position here where x is 4 is halved to 2, and this position here at 3 is halved to 1.5. And one more, our maximum here at 1 is halved to a half. So then we draw our function in using exactly the same curves and lines, except this time they are compressed. And you can see that that is half, that the overall dimensions of that are half the original dimensions. So the original dimensions are from -3 to 5, which is 8, and the compressed go from -1.5 to 2.5, which is 4. In green, to show you the difference, I'm going to show you f of a half of x. So this time k equals a half, which means it is expanded by a factor of 1 on a half. 1 divided by a half is 2. So what we're going to see here is the function is doubled. It's important to note that anything on the y-axis stays in the same spot for these horizontal dilations. All right, again, considering our point here at -3, it's doubled to -6. This maximum at -1.5 is doubled to -3. This root at 2 is doubled to 4. The maximum at 1 is doubled to 2. The endpoint at 5 is doubled to 10. This point at 4,2 is doubled to 8. This point at 3,1 is doubled to 6. And then we join them up. And you can see on this one that it's the same shape and it's the same height, but it has been stretched out to twice its original length. In the next example, 11.2, we'll have a look at how to do these algebraically.